Hi, I'm Lynsey Melville from Birmingham City University, and I'm leading the development of the scenario planning tools for the ALG-AD project. The ALG-AD project has a series of resources available for stakeholders. This includes a number of scenario planning tools in the form of reports, case studies, and online tools. These resources will help end users explore the opportunities and challenges of algal biotechnologies for nutrient uptake and animal feed production. The tools will help our stakeholders to identify potential opportunity sites via a map-based application, assess commercial viability of technologies via our techno-economic assessment, optimise future process designs, operations and performance using our process pathway tool, and also assess the environmental impacts and longer-term sustainability of the process using our life cycle assessment case studies. This tool allows us to selectively identify sites which offer the greatest opportunity for the implementation of algal cultivation. Using existing data sets, we have mapped the location of existing AD plants across a number of regions, the UK, France, Belgium and Germany. For this project, we are most interested in those within nitrate vulnerable zones to assess the potential of this technology to reduce eutrophication in these zones. We also want to identify AD plants which predominantly use plant-based feedstocks, as these are more suited to algal cultivation for animal feed. We also need to consider scale of the AD plants, so we can explore the scale of digestate supply within a region and to ensure that the photobioreactor process is commercially viable. We would also like to explore how we can use this data to inform decisions about the location of algal cultivation plants and enable better integration of supply chains. In order to evaluate commercial viability, the team has collected data from each of the pilot plants. This data includes the cost of construction, the materials, equipment and labour, of operation, the energy, water and other resources, and the overall rate of return on the pilot plants. The key findings, as well as the techno-economic assessment, is being integrated into an online tool which will enable stakeholders to explore the commercial viability of a project based on their own unique conditions and circumstances, and also assess the risks and sensitivities which influence the economics over time, for example, changing incentives or market fluctuations. A report on the macroeconomics of the process is also being completed, which will consider the market opportunities and challenges. So to give some examples, Langage is one of our UK-based AD plants and pilot plants. We've been collecting data on Langage pilot for over 2 years, and this data has been fed into our techno-economic assessment and our life cycle assessment. Some of the key findings from this assessment are that we know that in terms of income from AD, 75% of total income currently comes from the sale of electricity to grid. There is an additional income stream from gate fees, which makes up around 20% of total income. A small percentage from heat used within the plant, and the income from fertiliser sales represents around 2% of the total income. Some of our key findings are that sale of biofertiliser is an important revenue stream for Langage Farm. The biofertiliser is also used on the farm for soil enhancement. The project demonstrated that 2% of the digestate could be diverted to the photobioreactor to cultivate microalgae, increasing to potentially 10% with optimised operation. So for bioremediation perspective, this is quite a small percentage. Therefore, the value of the algal biomass is an important economic driver. The assessment explored the various market routes, utilising whole algal biomass as a feed or extracting high-value ingredients from the feed. It was found that the wholesale biomass couldn't really compete with existing animal feeds such as soya meal currently, but there was good opportunity to extract high-value products. 2 economic scenarios were explored: the construction of the AD and photobioreactor together, and the construction of a photobioreactor retrofit to an existing AD plant. Obviously, retrofit is more cost effective, assuming that there's sufficient space and infrastructure for the PBR facility. As part of the techno-economic assessment, we identified the hotspots with regards to high construction or operational costs. Some of the recommendations of the assessment were that the facility could be more economical if, for example, tubular components were made of glass rather than plastic. This would have an increased cost initially, but would have longer life and requires less cleaning and maintenance. Cost could also be reduced by recirculating the process water within the system rather than using potable water for dilution. Also, utilising excess electricity and heat from AD would be beneficial. The life cycle assessment explored the environmental impacts of the technology and process. LCA is used to assess environmental impacts at all stages of the product's life. It enables us to identify issues in design and configuration and also opportunities to improve the long-term sustainability of the process. ALG-AD systems are split into 3 distinct subsystems that contain individual processes. The design of the LCA is flexible so it can be adapted as the project progresses or as the process is optimised. As an example, this is the lifecycle assessment system boundaries for our pilot plant at Langage Farm. We have 3 subsystems currently: the AD plant, the membrane filtration process to pre-treat the digestate, and then the inoculation, PBR and harvesting of algal biomass. A 4th subsystem is also being developed around downstream processing of the algal biomass to convert it to animal feed. Once you've defined the system boundaries, you can capture the inputs and outputs of the process. So we have collected data on materials and resources, the energy, water and chemicals, for example, and also the emissions to air, water and soil. For the purposes of this analysis, the functional unit is 1 metric tonne of dry algal animal feed. These are the impact categories used in the life cycle assessment. These are standard for LCA and include, for example, impact resulting from the use of resources, from land use, from emissions to freshwater sources or to atmosphere. And this is the output from the LCA for our pilot plant at Langage. The y-axis represents the total environmental impact of the process. The x-axis represents the different types of environmental impact category, for example, eutrophication or land use. The coloured bars represent the percentage of total impact for each of the parts of the process. So, for example, orange represents the AD process, royal blue is the photoautotrophic phase of the photobioreactor. This provides a visual representation of which part of the overall process has the biggest environmental impact across a number of impact categories. What we found from this analysis was the phototrophic phase, the PBR, has the largest environmental impact across most of the categories. This is primarily due to the PBR construction and the energy and water consumption during operation. For Langage, we found that the mixotrophic phase had the largest impact with regards to marine eutrophication and ozone depletion. This is due to the carbon source that is used to supplement the process. As part of the LCA, we conduct a sensitivity analysis to explore various scenarios for improving the sustainability of the process. This showed that, for example, using LEDs rather than fluorescent lighting for the PBR had less impact on the environment. As with the techno-economic assessment, we found that utilising excess heat and energy from the AD plant and reusing water from the process improved overall sustainability. The project has evolved a number of outputs and case studies based on the 3 pilot plants. So we have a number of databases, reports and case studies that will be available on the website and via the Decision Support Tool interface. We've also extracted and summarised all of the key findings from the TEA, LCA and mass energy balance, so all of the information about the design, construction and operation of the process and all of the resources and infrastructure considerations. And these are integrated into our process pathway tool. This tool will take the users through a series of queries and will capture information most pertinent to them. For example, their motivation for developing a PBR, their site conditions, for example, the scale and nature of the AD plant, and it will use this information to provide tailored recommendations. The process pathway tool will enable end users to explore appropriate technologies, options and configurations, explore the infrastructure requirements, explore potential outputs, i.e. remediation efficiency, end products and markets based on the inputs, e.g. the digestate characteristics, and also identify additional relevant resources standard operating procedures, regulatory information, and research papers. We will demonstrate the prototype of these tools in our workshop later today. Thank you for your time. I'll take any questions.